Every time you press the exposure button, you create an invisible force that can ionize matter and deposit energy into the human body. And if you don't know how to measure it, you can potentially be producing biological damage to yourself and your patient. My name is Lazar Lazarovsky. I've been a radiologic technologist since 2005. I'm the host of the Radical Life podcast and the creator of the 21-day Registry Review Challenge, a highly structured course that follows the ARRT specifications outline, is taught by over 40 instructors, and helps students reduce overwhelm, erase anxiety, and pass their registry exam with confidence. Today, we're going to cover the SI units of measurement as they relate to the biological effects of radiation. More specifically, we're going to discuss absorbed dose, dose equivalent, exposure, effective dose, and KERMA. As always, the concepts you need to remember are below this video, along with all the conversion charts and a registry-style exam based on everything we'll be discussing today. Now, before we begin, just keep this one major distinction in mind. Radiation measurements are divided into two categories, air and tissue. Exposure and KERMA describe radiation measured in air, while absorbed dose, equivalent dose, and effective dose describe radiation measured in tissue matter. The NCRP report number 184 is also important in our discussion because it uses effective dose as a major quantity for evaluating and comparing medical radiation exposure. But the report also makes an important point. Effective dose is not something that is directly measured by a machine. It is derived from other quantities using radiation and tissue weighting factors. So with that said, let's begin with the first quantity, absorbed dose. Absorbed dose is the amount of radiation energy deposited into a physical object or material per unit of mass after an exposure is made. In our case, the object or material we are most concerned about is the patient's body or tissue. So as ionizing radiation passes through the body, part of it is absorbed by the tissue while the rest is scattered or transmitted, meaning it passes through the patient. Now, whatever radiation is absorbed by the patient is responsible for biological damage. Okay, now let's see how we actually measure this. Absorbed dose is expressed in grays, but because most X-ray exams don't involve large doses of radiation, we often convert absorbed dose into subunits of gray, such as centigray, milligray, or microgray. This chart here shows the typical subunits and how to convert gray into each of those subunits. The PDF below this video is something worth downloading and printing out for your reference. Now, when you want to figure out absorbed dose, here's the formula that you're going to use. Take the energy expressed in joules and divide it by the mass of the tissue in kilograms. Your absorbed dose will then be expressed in grays or its equivalent subunit. Since 1 gray is equal to 1 joule, if we say that a patient received an absorbed dose of 8 milligrays, which is typical, what we are saying is that 0.08 joules of radiation energy was deposited into each kilogram of the patient's tissue. Putting the conversion chart to memory is helpful when solving for questions you might see on the registry because you'll know that 1000 milligray is equivalent to 1 gray. And that helps in converting it into joules, which would just be 8 milligrays divided by 1000. So here's a question to consider. If a tissue sample receives an absorbed dose of 50 milligrays, how much radiation energy was deposited per kilogram of tissue? Well, if we use our conversion chart and divide 50 milligrays by 1000, the answer would be A, 0.05 joules per kilogram. So to summarize, absorbed dose does not simply tell us that radiation was traveling toward the patient and made contact with them. It tells us that radiation energy was actually left behind or deposited inside the patient's tissue. And if you remember from the Principles of Radiation Physics series, as an X-ray photon enters the patient, it may transfer its energy through interactions such as the photoelectric effect or Compton scatter. During the photoelectric effect, the photon transfers all of its energy and is completely absorbed, whereas with Compton scatter, the photon transfers part of its energy to an electron which can deposit some of it within the patient. The total energy deposited per unit of tissue mass is the absorbed dose. As an illustration, you can think of it like rain falling onto a sponge. The rain moving through the air represents radiation traveling toward the patient, but the water that remains inside the sponge represents the energy that was absorbed. Absorbed dose is not concerned with how much rain passed nearby. It is only concerned with how much water remained within the sponge. Pretty simple. Now, why does absorbed dose matter when we're discussing biological effects? Well, because absorbed dose is the measurement most directly connected to how much ionization occurs. And as we know, increased ionization creates a greater possibility of cellular or tissue damage, something we definitely want to monitor and keep track of. Absorbed dose is therefore especially useful when we are evaluating tissue reactions or short-term radiation effects. Examples include skin erythema, hair loss, changes to blood-forming tissue, and other effects that may occur after a sufficient amount of energy is deposited. Okay, with that said, let's talk about the 4 factors that can affect absorbed dose. These are MAS, KVP, distance, and tissue type. We start with MAS. MA, along with exposure time, affects the number of photons produced. If MAS increases and everything else remains the same, more photons are directed toward the patient. More photons create more opportunities for interactions. More interactions can deposit more energy. Therefore, absorbed dose increases. The second factor is KVP. Increasing KVP can increase both photon energy and the number of photons produced. If all other variables remain unchanged, that can increase the number of radiation reaching and interacting with our patient. So increased KVP equals increased absorbed dose. Third is distance, and it works in the opposite direction of KVP and MAS. When the distance from the source increases, the beam spreads out. The intensity decreases according to the inverse square law, which we covered in the principles of radiation physics. As beam intensity decreases, the amount of radiation available to deposit energy also decreases. So when we increase distance, we decrease absorbed dose. There's an inverse relationship there. Lastly, the type of tissue itself also matters. Tissues with greater density and higher effective atomic numbers absorb more radiation than tissues with lesser density and lower atomic numbers. That's why bone, muscle, fat, and air do not all receive or absorb energy in exactly the same way. But we have to remember the one major limitation of absorbed dose. It does not tell us how biologically damaging the type of radiation may be. 2 people could receive the same absorbed dose in gray and still experience different amounts of biological damage if radiation types were different. And that brings us to the next measurement, dose equivalent or equivalent dose. Now, just briefly, while these phrases sound almost identical, there is a historical difference. Dose equivalent is an older radiation quantity that was associated with quality factors and linear energy transfer. Equivalent dose is the current quantity that uses a radiation weighting factor. Equivalent dose begins with absorbed dose, but then it asks another question. What type of radiation produced that absorbed dose? Why does that matter? Because different kinds of ionizing radiation do not produce the same amount or concentration of biological damage. Imagine that 2 people each receive an absorbed dose of 10 milligrays. The physical energy absorbed per kilogram of tissue may be the same, but suppose one dose came from diagnostic X-rays and the other came from alpha particles used in targeted alpha therapy. Are those 2 doses biologically equivalent? Well, let's take a look at the data chart adapted from the International Commission on Radiological Protection. X-rays have a weighting factor of 1, whereas alpha particles seen down here have a weighting factor of 20. If that person we just mentioned received a dose of 10 milligrays with a weighting factor of 20 and the other with a weighting factor of 1, would the doses be biologically the same? No, right? Alpha particles have a much higher linear energy transfer than X-rays do. That means they deposit their energy more densely along a shorter path. X-rays have a lower linear energy transfer, so their ionizations are generally spread out over a greater distance. The absorbed dose of 10 milligrays may be the same, but the pattern of ionization and the biological effectiveness are not equal. That is why applying the radiation weighting factor is so important. Now, if we were to determine what the equivalent dose was, we would use the following formula. Equivalent dose equals absorbed dose multiplied by the radiation weighting factor. Now, while the equivalent dose is measured in sieverts, we will commonly use millisieverts in diagnostic X-rays to express the equivalent dose. All right, so let's try an example. Suppose a radiologic technologist receives an absorbed dose of 5 milligrays from X-ray scatter. The radiation weighting factor for X-rays is 1. So 5 milligrays multiplied by 1 equals 5 millisieverts. Notice what happened here. The numerical value remained the same. 5 stayed 5, but the unit changed. We went from milligray to millisievert. Why? Because we are no longer describing only the physical energy absorbed. We are now expressing that dose in terms of the biological effectiveness of the radiation type, the radiation weighting factor. Gray describes absorbed dose, sieverts describes weighted biological effect of that energy. Now imagine that the same 5 came from protons. What would the radiation factor be? Well, let's look at our chart. The radiation weighting factor is 2, so let's plug in the numbers. 5 multiplied by 2 gives us 10 millisieverts. Same absorbed dose, different radiation type. Very different equivalent dose to our technologist. That is the entire purpose of equivalent dose. It makes different radiation types comparable based on their relative capacity to produce biological damage. One other thing to remember is that equivalent dose does not yet account for which organ tissue received the radiation. We'll get to that a little later. But it only accounts for the absorbed dose and the radiation type. That's it. All right, so we talked about absorbed dose, that's the energy deposited per kilogram of tissue measured in milligrays. Then we moved on to equivalent dose, which takes that same absorbed dose and adjusts it based on the type of radiation involved. Was it diagnostic X-rays using photons? Was it targeted alpha therapy using alpha particles? Was it radiation therapy using protons? The types of radiation matter, and the result of that adjustment gets expressed in sieverts. Now, we still need another measurement to account for the fact that some tissues are more radiosensitive than others. But before we get to that measurement quantity, for the sake of following the ARRT specifications outline, we're going to move from measuring radiation in tissue or matter to measuring radiation in air. And the first of the two is exposure. Exposure is one of the most commonly misunderstood words in radiography because we use it, casually in several different ways. We may say that we are making an exposure. We may say that a patient was exposed to radiation. We may discuss occupational exposure. But when the word exposure is used as a specific radiation quantity, it has a very precise meaning. Exposure measures the electrical charge produced by ionization in a specific mass of air. Here's the basic idea. When a volume of air gets hit with X-rays or gamma rays, that radiation interacts with the neutral atoms in the air and knocks electrons loose, ionizing them in the process. Once that happens, the air isn't just sitting there anymore. it can actually conduct electricity because now you've got negatively charged free electrons and positively charged ions floating around. And here's the key relationship. The more intense the X-ray exposure, the more of these electron-ion pairs get created. So if we measure how many electron-ion pairs show up in a defined volume of air, we can actually work backwards and figure out how much radiation caused that ionization. That whole process is what we call exposure, which is measured in coulombs per kilogram in the SI system. For the sake of clarity, let's break down the coulomb. It's the basic unit of electrical charge, the amount of charge that moves past a point in a conductor in just 1 second when there's a current of 1 ampere flowing. Now, the ampere itself is the SI unit for current, and current is really just a charge that's on the move, usually in the form of electrons, each carrying a charge of negative 1.6 times 10 to the negative 19th power coulombs. So really, the ampere is just telling us how fast the charge is flowing. Now, if we were to solve for exposure, the formula would be as follows. Exposure equals charge divided by mass of air, where the charge is measured in coulombs and the mass of air is measured in kilograms. Once we divide charge by mass of air, we're left with the exposure measured in coulombs per kilogram. So coulombs per kilogram tells us how much electrical energy was produced by ionization in a kilogram of air. In a snapshot, here's what happens. An X-ray photon travels through the air and interacts with an atom. The photon transfers enough energy to remove an orbital electron. We now have a negatively charged electron moving away from the atom and a positively charged atom that has lost an electron. Together, those charged particles form an ion pair. Exposure is based on the charge produced by those ionizations in air. Everything is happening within the space of air before it interacts with any matter. That is the main idea. Exposure equals the charge that exists within air, and it's measured using an ionization chamber. An ionization chamber is basically a tool that measures radiation by using ionization itself. Inside the chamber, you've got a known volume and mass of air, or another gas. When X-rays or gamma rays pass through, they ionize the atoms inside, freeing up electrons and creating positive ions. Those freed up electrons and ions get collected by two oppositely charged plates, and from there we can measure that electrical charge and express it in coulombs per kilogram. What makes this so useful is that it gives us a way to evaluate the intensity of an X-ray or gamma ray field without having to count every single photon traveling through the air. The ionization itself tells the story. Pretty cool. If more photons are present, more ionizations can occur. If more ionizations occur, more charge is collected. And if more charge is collected per kilogram of air, the exposure measurement increases. And just as with absorbed dose, the same factors of MAS, KVP, and distance affect exposure in the same exact way. Increasing MAS increases the number of photons. More photons create more ionizations, therefore exposure increases. Increasing KVP can also increase the number and energy of the photons in the beam. If everything else remains unchanged, exposure can increase. Distance decreases beam intensity because the photons spread over a large area, think inverse square law, produces fewer ionizations in the measured volume of air. Therefore, exposure decreases. Exposure can be used when evaluating X-ray tube output, leakage radiation, and scatter radiation in air. But it has its limitations as well. It applies to ionization produced by X-rays and gamma radiation in air. It does not directly tell us how much energy will ultimately be deposited inside a specific organ or how much biological damage will occur. And in modern imaging, exposure is increasingly replaced by another quantity that measures radiation in air more directly in terms of energy. That quantity is air KERMA, which we'll cover last since we're following our trusty specs outline here. Okay, so far we've discussed absorbed dose, which is the energy deposited into tissue, and it's measured in gray. Equivalent dose adjusts the absorbed dose according to the radiation type, and it's measured in sieverts. Exposure measures the electrical charge created by ionization in air, and it's measured in coulombs per kilogram. Now, let's get back to the patient and account for one more biological factor: the radiosensitivity of the tissue that was exposed. That brings us to effective dose. Effective dose is one of the best quantities for understanding the potential, keyword potential, long-term biological effects of radiation exposure to humans. It takes the information we already have and adds another layer to it. Absorbed dose tells us how much energy was deposited. Equivalent dose accounts for the type of radiation. Now, effective dose accounts for the type of radiation and the radiosensitivity of the tissues and organs exposed. The NCRP report number 116 defines it as the sum of the weighted equivalent doses for all irradiated tissues or organs. So the formula for effective dose then is the sum of each tissue's equivalent dose multiplied by its tissue's weighting factor. For a simplified situation involving one tissue and one radiation type, you may see the formula written as follows. Effective dose is equal to absorbed dose multiplied by radiation weighting factor multiplied by the tissue weighting factor. The SI unit for effective dose is the sievert, which is the same unit used for equivalent dose. But even though the units are the same, the quantities are not the same. Equivalent dose considers radiation type. It's talking about only radiation. Effective dose considers both radiation type and tissue sensitivity. So it takes into account both weighting factors. Here's a practical example that I think will help. Imagine that two patients each receive an absorbed dose of 10 milligray from an X-ray exam. One receives the dose to the brain, while the other receives the dose to the gonads. The absorbed dose is exactly the same, 10 milligray. The radiation type is the same, diagnostic X-rays. The equivalent dose is also the same, but is the estimated or potential long-term biological risk the same? Well, that's where the tissue weighting factor comes into play. If we look at our chart here, different tissues have different levels of radiosensitivity. So estimated long-term biological risk is not the same. The tissue weighting factor represents the relative contribution of a particular organ or tissue to the total risk of stochastic effects, such as radiation-induced cancer. A tissue with a higher weighting factor contributes more to the effective dose. A tissue with a lower weighting factor contributes less. As you can see here, the effective dose to the gonads is much higher because the gonadal tissue has been assigned a higher tissue weighting factor. Now, that does not mean that every individual exposed will experience that exact biological outcome. It means that the tissue makes a greater contribution to the estimated or potential overall long-term risk. It can only give an estimated or potential risk factor, not a precise one, and we'll see why in a moment. But just briefly worth noting, when all of these tissue weighting factors are combined, they equal 1. Why is that important? Because the numbers allow a partial body exposure to be expressed in terms of its estimated contribution to overall whole body risk. Now, this is where the NCRP report number 184 becomes especially relevant. NCRP report number 184 uses effective dose as a central quantity when comparing medical radiation exposure from different procedures and estimating exposure across groups and populations. But it also makes it clear that effective dose is derived, meaning it's calculated using math and models such as phantoms. It's not measured directly with instruments such as ionization chambers or a dosimeter. Instead, measurable quantities for effective dose are obtained using conversion factors, radiation weighting factors, tissue weighting factors, and models such as phantoms in place of people. This gives us the following progression. First, something is measured, Then organ or tissue doses are estimated. Then radiation type is considered, followed by tissue sensitivity, and the result is the effective dose. But there is another important point from this report. Effective dose is useful for radiation protection, comparison, and optimization. It can help compare the general radiation exposure from different imaging procedures. It can help compare one modality with another, and it can help evaluate population exposure patterns over time. But it should not be treated as a perfect prediction of one individual patient's personal cancer risk. Why not? Because each person is uniquely created. Age, sex, body size, environment, genetics, anatomy being exposed, technique being used, all of these factors can and often are different. Not to mention that each individual has different biological characteristics. So the tissue weighting factors used in effective dose calculations are population-based values. They are not customized risk factors created for each individual patient. The NCRP report number 184 therefore cautions that effective dose should not be used to determine precise individual risk. It is better suited to comparing exposure and guiding radiation protection decisions across procedures or populations. That distinction between individuals versus general population and estimated versus precise is huge. So, effective dose is an estimate of overall radiation detriment. It's not an imaginary crystal ball that gives us precise measurement of dose. It can tell us that one examination generally produces a greater or smaller radiation burden than another, but it cannot tell an individual patient with absolute certainty what will happen to them. Okay, so far we've discussed absorbed dose, which measures energy deposited in tissues using grays. Equivalent dose, which takes that absorbed dose and adjusts it for the radiation type using a radiation weighting factor expressed in sieverts. Then we talked about exposure, which measures the electrical charge produced by ionization in air expressed in coulombs per kilogram. And then we just talked about effective dose, which takes the equivalent dose to the exposed organs, adjusts them using tissue weighting factors, and expresses the overall estimated biological harm in sieverts. That leaves us with one final quantity, KERMA. KERMA is another SI quantity that is used to express how energy is transferred from radiation to air. The word KERMA is an acronym that stands for kinetic energy release per unit mass. The main idea is that KERMA measures the kinetic energy transferred by ionizing radiation to charged particles in air using an ionization chamber as the instrument that can be calibrated to read it. When an X-ray photon interacts with an atom in the air, it has the ability to remove an electron. When that happens, some of the photon's energy is transferred to that electron. That electron then moves through the air with kinetic energy, which is just a fancy way of saying energy in motion. KERMA describes the amount of that kinetic energy transferred to the charged particles per unit mass of air. The SI unit of KERMA is expressed in grays. As we know, 1 gray is equal to 1 joule per kilogram. Just like absorbed dose, KERMA may commonly be expressed in milligray or microgray during medical imaging because 1 full gray is a very large quantity that's not really used in standard X-ray procedures, as we said earlier. Now, this is where students commonly get confused, so it's important to really pay attention here. Absorbed dose and KERMA are both measured in gray. So are they the same thing? No, the same unit does not mean the same quantity. Absorbed dose describes energy deposited in tissue or another material. KERMA, on the other hand, describes energy transferred to charged particles in air. Here's a simple way to remember the difference. Absorbed dose is the energy that remains in tissue. KERMA is the kinetic energy that's released in air. So you see, they use different media. One uses tissue, the other uses air. The reason they're both expressed in grays is because both involve energy per unit mass. Exposure and air KERMA are also closely related, but they are not identical. Exposure measures the electrical charge produced by ionization in air, and its unit is coulombs per kilogram. Air KERMA, on the other hand, measures the kinetic energy transferred to charged particles in air. So exposure equals the charge measured in air, while air KERMA equals the energy measured in air. That is probably the easiest way to separate the two, but here are some similarities with minor variances. Just like exposure, air KERMA is measured using an ionization chamber. Radiation passes through a known volume of the air and produces ionization. The chamber collects the electrical charge. When the instrument is calibrated to report that charge per mass of air, it can provide exposure. When calibration factors are applied to express the energy transferred per mass, it can provide air KERMA. Air KERMA is also affected by the same general factors that affect exposure. If MAS increases, more photons are produced. More photons can transfer more energy to charged particles in the air. Therefore, air KERMA increases. Likewise, if KVP increases and all other factors remain unchanged, the number and energy of photons increase. What happens to air KERMA? It also increases. Lastly, if distance increases, beam intensity decreases according to the inverse square law, which means less energy is transferred within the measured mass of air, resulting in a decrease in air KERMA. Air KERMA is useful when evaluating X-ray tube output, scatter radiation, leakage radiation, and the radiation incident on or near the patient. It also appears in modern fluoroscopic and radiographic dose metrics. The NCRP report number 184 includes air KERMA-based quantities among the recommended metrics for medical imaging procedures. Its table of recommended quantities includes air KERMA measurements for radiography, mammography, fluoroscopy, and related applications, generally expressed in milligray or gray depending on the procedure. This helps explain why air KERMA has increasingly replaced exposure as the preferred method for describing radiation in air. Now, one last thing that we need to know before wrapping up is dose area product, or DAP. DAP is a little different from what we've covered so far. Instead of just measuring dose at a single point, it factors in the size of the area being exposed as well. Essentially, it's the total air KERMA summed across the entire exposed surface of the patient, a way of capturing how much radiant energy was delivered to that portion of the body. It's calculated by multiplying air KERMA by the exposed surface area, and it's expressed in units of milligray centimeters squared. So, say a patient's skin receives an air KERMA of 8 milligrays over an exposed area of 300 centimeters squared. That gives us 8 milligrays times 300 centimeters squared equals 2,400 milligrays centimeters squared. That single number represents the total radiant energy delivered to that portion of the patient's body. And here's why DAP matters in the context of everything we've covered so far. It's one of those measurable quantities we talked about earlier, something an ionization chamber or built-in detector can actually record directly, right there on the machine. From that single DAP value, we can apply conversion factors and models to estimate organ doses and ultimately work our way toward an effective dose. So DAP isn't just a standalone number. It's often the starting point of that whole progression. Measure something, convert it, determine its weighting factor, and arrive at the effective dose. All right, let's wrap up by bringing all of the 5 SI units of measurement quantities together with this memory chain I want you to walk away with. Energy absorbed in tissue gives us absorbed dose in gray. Adjust that absorbed dose for radiation type, and we have equivalent dose in sieverts. Measure the electrical charge created in air, and we have exposure that's measured in coulombs per kilogram. Adjust equivalent dose for tissue sensitivity, and we have effective dose in sieverts. Measure kinetic energy transferred in air, and we have air, KERMA, and gray. Gray means energy per mass, sievert means biologically weighted dose, and coulombs per kilogram means ionization charge in air. Master those 3 units and understand what question each quantity answers, and SI units of measurement becomes much easier to identify. And remember, don't simply memorize that absorbed dose equals gray or effective dose equals sieverts. Ask yourself, are we measuring radiation in air or tissue? Are we measuring charge or energy? Are we accounting for radiation type? Are we accounting for tissue sensitivity? Or are we accounting for both type and tissue factors? When you can answer those questions, you won't have to guess which measurement belongs in which situation. You'll understand why it belongs there. If you want to master the concepts you learned here today, take the free exam provided for you in the link below. Teach what you learned here to someone else. And if you need help passing the ARRT registry exam, check out the 21-day registry review challenge at radtechregistry.com. Lastly, don't forget to share this lesson with someone you like, hit the subscribe and notification button, and speaking of like, don't forget to do the same for this video. As always, thanks for watching, and I'll see you in the next one.